a quick note about today's quest. It will not be on ALEKS. Today's quest will be on Moodle. And so there's a link to it on our Moodle page. It is in the quest section, remote quest work section. And there's a place for the quest 5. And then there's also a place for you to upload your scratch work. Okay. Now this is a little different for us, right? Because it's on Moodle instead of on ALEKS. It's just I had already written a nice quiz that I liked, nice quest that I liked in the Moodle format, and so we're going to do that today. It's 15 questions. A little more than half of them are just sort of theory and concept. You know, what is equilibrium? Which way does the equilibrium shift? That kind of thing. And there's maybe 5 or 6 calculation-based questions. It's open from 10:25 to 5 p.m. today, and it has a 45-minute time limit. So everything else is the same, just like ALEKS. Same time frame, same time limit, same number of questions, same number of points, all that kind of stuff is the same. It's just on Moodle instead of on ALEKS. Okay.
Dr. Davis.
Yes.
Will we still get our scores back immediately like we do on ALEKS?
Yeah, so you'll get the number of points immediately. It won't show you the right and wrong until after the quest closes.
So at 5:02 or something, we would be able to see like how, like we would get our score immediately, but we would be able to see like how we did.
Right. Yep.
And we would potentially be able to see like where we would get partial credit for our scratch work.
Right, absolutely.
Perfect. Thank you.
Yep. All right. So that's the quest. We finished up talking about chapter 14 and equilibrium stuff on Wednesday, and so you know, the quest today is almost all equal. Well, it is all equilibrium, and it covers almost all of chapter 14. There's one bit of chapter 14 that we didn't talk about in class, and so we're going to talk about that today. We're going to sort of wrap it into the chapter 15 stuff, since chapter 15 continues to talk about equilibrium. So let's get into it. We have, chapter 15 is talking all about acids and bases, and it starts off very broadly and generic, and then towards the end of the chapter, we may not get to it today, but towards the end of the chapter, it breaks into equilibrium and how equilibrium ties into acids and bases. Okay. All right. So, acids. Some things about acids. While we shouldn't taste things in lab, there are acids that are foods. And so what do we know about acids and their taste?
Sour.
Yeah, absolutely. And so these are a sour taste, right? Think things like pickles, vinegar, orange juice. A chemical thing about acids is that they react with a lot of metals to give off hydrogen gas. Not all metals, but with lots of metals. So that's a key characteristic of acids. Remember, acids give up protons in water, and so if we've got lots of protons around, they'll join up to form hydrogen gas. Bases, who knows anything about how bases taste?
Bitter.
Yeah, for sure. Bases have bitter taste. So the basic thing that I think of when I think about tasting is like if you've ever bitten into an orange rind, like not an orange, but you've ever gotten a little bit of the rind in your mouth, that has a lot of organic bases in it, and that's the bitter flavor that I think about. If you've ever had tonic water, that has quinine in it. Quinine is a base, and tonic water is quite bitter if you have it by itself. Another thing about bases is that they react to break down fats, and so they break down fats into soap. So if we have a strong base, it'll break down any fat or any oil into soap. And that's why when you get a strong base on your hand, your skin feels a little slippery, right? That the reason is that the base is turning the oils on your fingers into soap. Not to get all Fight Club on you, but that's what's happening when you get some base on your hand. And so that's one of the reasons why soaps and Windex and things like that, that's why they feel a little slippery. All right, so we have a couple of definitions of acid and base. The one that we're going to stick with is Bronsted acids and bases. We talked a little bit about this, having Arrhenius acids and bases, Bronsted acids and bases, Lewis acids and bases. We're going to stick with Bronsted acids. And our definition of a Bronsted acid, do you remember what he gives up if he's a Bronsted acid?
Hydrogen.
Proton.
A hydrogen, a proton, yeah, all of these are good things. And so we think about acids as being a proton donor, which is H plus. Right? And so then a base in this Bronsted description is a proton acceptor. So we've got this reaction here between NH3 and water, and that reaction gives us NH4 plus and OH minus. If we look at this, which of these two reactants, NH3 or H2O, which of those two is donating a proton?
H2O.
Yeah, so H2O is our acid, right? He donates a proton. And then NH3 is our base because he accepts a proton. NH3 becomes NH4 plus, H2O becomes OH minus. Remember, it's not just a hydrogen, it's got that plus charge. And so we need to make sure that our charges end up correct. If we look at the other side, excuse me, if we look at the other side of our equilibrium, now this is an equilibrium, it's not a one direction arrow. But if we look at the other side, we have NH4 plus and OH minus. Right? And so think for a minute about this reaction going the other direction. So it's gone forward and we said that ammonia is the base and water is the acid. If we go the other direction, which of these two compounds is behaving as the acid if we go from right to, if we go from right to left?
NH4 plus.
Yeah, NH4 plus is our acid, but he's not part of our reactants, and so we call him a conjugate acid. Right? So the base and the conjugate acid, right, differ by one proton. And if we look at the other, if we look at the right side again, our OH minus is behaving like a base. And so he's the conjugate base. And between the acid and the conjugate base, we lose a proton. If we're looking at the reaction from right to left. Okay. And so in a lot of these acid-base reactions, we'll talk about conjugate pairs, right? And so anytime we talk about conjugate pairs, the acid or the base is always in the reactant side, and then the conjugate is always on the product side, right? Even though they're really an acid and a base in both places, we just name the one that's in the reactants the conjugate. So if we look at this reaction between ammonia and HF, hydrofluoric acid, this one's not too different from what we just looked at. So which is our base here?
NH3.
Yeah, NH3 is our base. Bases were blue. Which makes what our conjugate acid?
NH4 plus.
Yeah. Our ammonium is our conjugate acid. And so then that must mean that HF is our acid. Acids are usually easy to identify by that H out front, right? Making F minus our conjugate base. Okay. Not too bad. So if we were just given a base, for example, what would be the conjugate acid for OH minus?
H2O.
Yeah, remember going from base to acid means we just add a proton. So H2O going from hydroxide to water. How about with this bicarbonate ion?
H2CO3.
Excellent, excellent. And then this last one, if we add a proton to water, we get H3O plus. We have a special name for this ion. Does anybody remember?
Is it hydronium?
Hydronium, yeah. The hydronium ion. We'll see a lot of him in this chapter. And so for conjugate bases, right, we just remove protons. And so HCl becomes Cl minus, HCO3 becomes CO3 2 minus, H2SO4. Now remember, we're just removing one proton. And so H2SO4 does not become SO4 2 minus, but HSO4 minus. All right, something to point out real quick. We have bicarbonate on the acid side, or sorry, on the base side, and bicarbonate on the acid side. Right? And so bicarbonate is what we call amphoteric. That means that he can behave either as an acid or a base. Right? On this slide, we've got two other amphoteric species. Water here is behaving like a base, taking a proton. Here, water is the conjugate acid of OH minus, and so he's the acid there. And so water can behave either way, like an acid or like a base. HSO4 is another one. He can lose another proton to become SO4 2 minus, or he can gain a proton back to become H2SO4 again. And so these amphoteric species are species that can kind of go either way. They can either be acids or bases. We're going to spend a good bit of time talking about water, and so let's go ahead and get into it. Acid-base properties of water. Water can react with itself to give us H3O plus and OH minus, right? So this is H2O, H2O in equilibrium with H3O plus and OH minus. We call this the auto-ionization of water. Right? Auto because he doesn't need to have something other than water in solution. Even if we have just a pure water solution, some of that water is going to split apart into H3O plus and OH minus. And so again, water is behaving as an amphoteric species. We end up with both positive and negative ions in solution. Right? Now, H3O plus is just another way of writing H plus. And so I'm going to write that this is equivalent to H plus. Because we could write this autoionization of water as H2O is in equilibrium with H plus and OH minus. Right? That is another perfectly acceptable way of writing this autoionization. And so when we look at H plus or H3O plus, know that those are interchangeable when we're talking about the proton when it's in an aqueous solution. All right, so since this is an equilibrium, let's talk a little bit about equilibrium. And we call it in particular the ion product. And so the ion product constant Kw, so we've seen K before, we've seen Kp, and we've seen Kc. This is the first time for Kw. The W is just for water. And it gives us the concentration of H plus and OH minus at a particular temperature. And so the equilibrium constant for this reaction is defined as Kw. And what's it equal to? How do we write this Kc expression, Kw expression? Good review for the quest today.
The concentration of H plus times the concentration of OH.
Yeah. Why do we need the water?
Because it's a liquid.
Yeah, anytime we have a pure liquid or a solid, remember we're going to ignore those in our K expressions. And so this Kw is just equal to the concentration of H plus times the concentration of OH minus. Right? Since these are constants, right, we know what Kw equals. And so at 25 degrees C, and we always have temperatures associated with equilibrium constants, Kw is equal to 1 times 10 to the negative 14. No units there, right? Now, if we are in a pure water solution, then the concentration of H plus has to equal the concentration of OH minus. If water breaks apart, if one water molecule breaks apart, we get one of each. If 17 water molecules break apart, we get 17 of each. If a billion water molecules break apart, we get a billion of each, right? And so if there's only water in our solution, then those two concentrations have to be the same. And if those two concentrations are the same, what do we say about that solution in terms of acidic or basic?
Would it be neutral?
Yeah, absolutely. This is a neutral solution. If we have more H plus than OH minus, so we're not in pure water anymore, but if we have more H plus in solution, what kind of solution is that then?
acidic.
Yeah. And then if we have more OH minus than H plus, we call that basic. Okay. So if we know, so let me back up just a minute. Even though that this is the only one that is pure water, right? This Kw is true no matter what the solution is. Even if the solution is not pure water, if our solvent is water, the water that's making up the solvent is still going to be in this equilibrium. That equilibrium might be shifted based on what's in solution, but it's still going to be in equilibrium. And so this Kw applies to all solutions containing water. And so with that in mind, we can do some problems. So the concentration of hydroxide ions in ammonia cleaning solution is 0.0025 molar. Calculate the concentration of H plus. If we set it up, Kw is equal to H plus times OH minus equals our unknown H plus times 0.025 molar, 0.0025. And we know Kw is 1 times 10 to the negative 14. Right? Similarly, down here, we know that Kw is equal to H plus times OH minus is equal to 1.3 times our hydroxide solution. Right? So H plus concentration in our ammonia solution, who's got it?
I got 7.69 times 10 to the negative 15th.
I got 4.0 times 10 to the negative 12.
Yeah, something funny happened there, Jack. Check your math again. 4.0 times 10 to the negative 12 molar. And how about on the bottom? Or were you answering for the bottom, Jack?
I did the bottom one. That's my bad.
Yeah, no, that's fine. That's fine. As soon as I moved my glance, I figured that's what you had done. So 7.7 times 10 to the negative 15 molar is our OH minus concentration. And so the larger the concentration of the acid or the base in our water, the less the concentration of the opposite ion, right? Either H plus or OH minus. Okay. All right. So what do we do with these values, right? Once we find these concentrations, what do we do with them? Well, we are going to talk about pH, and that's how we're going to talk about acid and base strengths, right? And so how acidic is a solution? We're going to look at pH. And so for us, pH is equal to the negative log of the concentration of H plus. And so the P part there is just has to do with the math that's being done. And so pH is negative log of the hydrogen concentration. pOH is the negative log of the hydroxide concentration. If we had pCa, right, that would be the negative log of the calcium ion concentration. And so the P just means take the negative log. And so if we have a neutral solution, right, we've talked about how that means that the concentration of H plus is equal to the concentration of OH minus. Now, if we were to plug in and for a pure water solution, calculate the concentration of H plus, let me do that over in this corner. So 1 times 10 to the negative 14 is equal to the concentration of H plus. Now, knowing that H plus is equal to OH minus, I can just say times the concentration of H plus, right? Because the concentration of OH minus equals the concentration of H plus. And so the concentration of H plus is just the square root of 1 times 10 to the negative 14. So that's 1 times 10 to the negative 7 molar. And so our hydrogen ion concentration is 1 times 10 to the negative 7 molar. And if we take the pH of that, negative log of 1 times 10 to the negative 7 is just 7. And so that's a nice shortcut, right? If your concentration is 1 times 10 to the something, the pH is the negative of that something. That only works if it's 1.0, right? It doesn't work if it's fractions. So if we have a basic solution, that means that we have less H plus than we do OH minus. And so does that make our H plus concentration greater than or less than 1 times 10 to the negative 7?
Less.
Yeah, less than 1 times 10 to the negative 7. And that makes our pH value go up, right? Because it's the negative log, as our exponents get more negative, so 10 to the negative 8, 10 to the negative 9, 10 to the negative 10, as that concentration gets smaller, the negative log of that number goes up. And then, of course, if we're in an acidic solution, we have more H plus than we do OH minus. Our concentration of H plus is larger than in pure water. And so we have a pH less than 7. And so as pH goes up, the hydrogen ion concentration goes down. Okay. So let's do a couple of examples using this pH. The concentration of hydrogen ions in a bottle of wine was 3.2 times to the negative 4. Right after the cork was removed, only half the wine was consumed, amateurs. The other half, after it had been standing open for a month, was found to have a hydrogen ion concentration of 1 times 10 to the negative 3. Calculate the pH of wine on these two occasions. Like I told you at the beginning of the semester, my wife is from Spain, so wine's a big part of our household. I cannot imagine a bottle of wine lasting a month. So pH is equal to negative log of concentration, 3.2 times 10 to the negative 4. For the second one, pH is the negative log of 1.0 times 10 to the negative 3. 1 times 10 to the negative 3, I can do that one in my head. Remember, if it's 1 times 10 to the something, it's just the negative of that number. So that one has a pH of 3. How about the first one?
I got 3.5.
Yeah. So a word about sig figs for pH and with logarithms. The number of decimal places is equal to the number of sig figs okay. And when we talk about logs, that first number is called the characteristic. Everything after the decimal point is called the mantissa. Right? I don't know if you learned these back in algebra, but in any case, the number of sig figs after the decimal point, or the number of decimal points, I should say, is equal to the number of sig figs. And so since we had 2 sig figs in our concentration, we should have 2 decimal places in our answer. That first number does not count towards sig figs. Okay. All right. One more here. We have a nitric acid solution with a concentration of 0.76 negative log of 0.76 gives us
0.12.
0.12. Yeah. And so maybe you remember from somewhere that the pH range is 1 to 14, right? That is a common pH range, but we have acids that are stronger, that have pHs that are even below 0, right? pH of -1, -2, something like that. And then there are bases that are strong that give us solutions with pHs of 15, 16, 17. And so that 1 to 14 is a sort of a general trend. That's where a lot of solutions have pHs. But there are very strong acids and very strong bases that have pHs above and below that range. All right. So rainwater is collected in the northeastern United States, and that has a pH of 4.82. Calculate the hydrogen ion concentration. And so to go from pH to hydrogen ion concentration, remember negative log of the hydrogen ion concentration is pH. To do the anti-log, right, to get rid of the log on both sides, we raise 10 to them, right? And so we need to get 10 to the negative pH is equal to 10 to the negative log, right? So we need positive log in order to do this. And so we have to raise it to the negative power. So 10 to the negative log is 10 to the log of H plus. The 10 and the log cancel, and so we get our H plus concentration. So 10 to the negative 4.82 is equal to 1.5 times 10 to the negative 5 molar. Again, I have 2 decimal places in my pH. I'm going to have 2 sig figs. So we can go from concentration to pH, we can go from pH to concentration. We got to bring some of that 123 stuff back and now go from concentration into actual numbers of ions. And so we know that the pH is 3.33 and it gives us a volume. And so 10 to the negative 3.33 is equal to my H plus concentration, which is 4.68 times 10 to the negative 4 molar. And so how many hydrogen ions do I have?
Do you need to calculate the number of moles of hydrogen ions that you have?
Yeah. So you'll go from moles to individual pieces. Yeah. Individual ions. It's been a while, so if you don't remember Avogadro's number, 6.022 times 10 to the 23rd.
Was it 4.23 times 10 to the 10 to the 19th?
Times 10 to the 19th. Yeah. 4.23 times 10 to the 19th. Yeah. And I guess we should only have two sig figs here. 4.2 times 10 to the positive 19. So yeah, once we have the concentration, we can use volume to figure out the number of moles. Once we know moles, we can use Avogadro's number to figure out the number of ions. Right? Feeling good about that? Any questions about that? Okay, one more example with pH before we move on. In a sodium hydroxide solution, it gives us the hydroxide concentration of 2.9 times 10 to the negative 4, calculate the pH. Now, there's two different ways to do this, right? We can relate the concentration of OH minus to the concentration of H plus via Kw. And so we know that Kw is equal to H plus times OH minus. And so 1.0 times 10 to the negative 14 divided by 2.9 times 10 to the negative 4 equals our hydrogen ion concentration. .4 times 10 to the negative 11. And then we can take the pH of that. And we get 10.47. The other way to solve a problem like this, that's perfectly fine. If that makes sense to you, by all means do it. The other way to do a problem like this is, so we know that Kw has to equal the concentration of H plus times the concentration of OH minus. If we take the negative log of both sides, the negative log of Kw is the negative log of 1 times 10 to the negative 14. That's just 14. The negative log of H plus concentration is pH. And the negative log of OH minus, the negative log of OH minus is POH. And so we know that 14 is equal to the sum of pH and POH. Since we know that, we can just do 14 minus the negative log of 2.9 times 10 to the negative 4 to get our pH, and it better be the same answer. 10. All right, so I got off by one decimal, 1/100th when I counted for sig figs here. But still, we get a very, very similar number. Either way is a-okay with me. Right? This is a handy little equation to have in your back pocket. Right? The fact that pH and POH have to equal 14. Right? So go ahead and solve this next one. We have the pH, and we'll ask for the concentration of hydroxide ions. Again, you can do it either way. You can find the concentration of H plus and use Kw to find OH minus, or you can subtract to find POH and then find concentration of OH minus that way. Either way will work. Go ahead and give it a shot. hopefully if you did this, you got 2.6 times 10 to the negative 7th mole. Okay. All right. So that's all about pH. Now, pH tells us about how acidic a particular solution is. pH does not tell us how strong an acid or a base is. And I know that that seems a little counterintuitive. pH tells us all about acidity, not about strength. And so the way that we talk about acid strength is by talking about whether or not it's a strong electrolyte. So a quick reminder, we talked a little bit about this in chapter 12, but we have strong electrolytes. And what did we know about strong electrolytes? What made them strong?
They're soluble.
They're 100% soluble, right? They break apart 100% all the way. They dissociate 100%. So let me put that over here. 100% dissociation. Now, because they dissociate all the way, there's no going back to the solid, right? That's why this is a one direction arrow. It only breaks apart. It doesn't reform. Now, weak electrolytes, they partially dissociate. And if some of the compound is left as the whole molecule, and some of the compound breaks apart, then we're going to set up an equilibrium, right? We're going to get to this point where the concentrations don't change for the products and for the reactants. And so notice there we have our equilibrium arrow. When we talk about strong acids, we talk about those as being strong electrolytes. And so here is a short list of strong acids: HCl, HNO3, HClO4, and H2SO4, right? All of these are strong acids. Notice that these are, I don't want to confuse you, notice that these are all one direction arrows. You will need to know a short list of strong acids. These four plus HBr and HI, right? So there's only 6 strong acids that we need to know, right? If you see an acid, so if it has either an H out front or it ends with this COOH here, that's indicative of an acid as well. So if you see either one of those and it's not one of these 6, you know that that's going to be a weak acid. Weak acids don't dissociate completely, and so they set up an equilibrium. Some examples here: there are a ton of weak acids, only 6 strong acids, a whole lot of weak acids. And so we have HF, nitrous acid, HNO2, this bisulfate anion, right? Remember we said it could act as an acid or as a base. If it acts as an acid, it's a weak acid. And then water. We talked about water also being amphoteric, behaving both as an acid and a base, and it is a weak acid. Okay. On the other hand, we have strong bases as well. And so our strong bases, you should have this list. The strong bases are an easy one to memorize, and so it's group 1 hydroxides. Plus this barium hydroxide, right? Barium hydroxide is the only alkaline earth hydroxide that is a strong base. But all the group 1 hydroxides, lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, strontium hydroxide, cesium hydroxide, all those are strong bases. They break apart completely in water. Similarly, if it's not on that list, right, if it's not a group 1 hydroxide, and it's not barium hydroxide, then it's going to be a weak base. And there are lots of weak bases. F minus behaves like a weak base. NO2 minus behaves like a weak base. NH3 behaves like a weak base. I'm going to put water on here too, because water is one that we saw behave both ways. He made the weak acid list. Why not the weak base list? So he'll be on there too. And so some things to remember about these conjugate acid and base pairs. If we have a strong acid or a strong base, the conjugate is not strong whatsoever. And so I'm going to say and vice versa here. Because if we have a conjugate acid of a strong base, it also has no measurable strength. Right? So HCl, one of our strong acids, right? If we put sodium chloride in water and we get some Cl minus in water, that solution is not instantly basic whenever we put salt in there because of the Cl minus, because that Cl minus has no strength as a conjugate base. H3O plus, this hydronium, is the strongest acid that exists in aqueous solution. Right? The reason is whenever we put a strong acid into water, he gives up all his protons to water molecules. They all become H3O plus, and that's what exists in water. Right? If we have a pure solution of nitric acid, for example, it's a very strong acid, but as soon as we add it to water, there's no more nitric acid. Right? All the nitric acid has broken apart, and the only thing we have is a whole heck of a lot of H3O plus. The last point here, when we have hydroxide, it's the strongest base in aqueous solution. Same idea. Whenever we put a strong base into water, it instantly breaks apart, and we have that OH minus. That OH minus exists. Sodium hydroxide no longer exists. It's just OH minus. And so the hydronium and the hydroxide are the strongest acid and base, respectively, that we have in aqueous solution. All right, that's a good stopping point for today. We're out of time as well. Like I said, the quest opens up in 5 minutes. It is on Moodle, not on Alex. And so be sure that you go there instead of logging into Alex. All right. There's also a place to upload your scratch work. So if you have any, do that as well. Have a great weekend.
Thank you.
Thank you.
Thank you.